Welcome to the 25th lecture of the course Turbulence. So, in the last few classes we are talking about the wall bounded turbulent flows, and in the process we have considered the turbulent channel flow. And turbulent channel flow, if you remember that first we derive the shear stress relation, that is your this 1 minus y by delta, okay, where your tau Vt is rho nu del u del y minus rho u v bar. Okay. So, or we can write that as tau Vt by rho nu del u del y minus u v. Okay. So, very close to the wall we found that this viscous shear stress dominates, whereas as we go away from the wall that turbulence shear stress starts dominating. Okay. So, this is what we learned. Then we have also learned that very close to the wall the velocity is essentially scaled by your inner variables, or it scales with the inner variables. So, we found very close to the wall the law of the wall, as you can remember that f w is a function of this, and this particular function for y plus less than 5, we found that u plus is equal to y plus, and this relation holds good for y plus less than 5. Okay. Then we also found the log law, I mean, so that is your u plus is equal to 1 by kappa ln y plus plus that some constant b. Okay. So, this is what is our log law. Okay. So, these are the main things we have discussed, along with the Reynolds stresses, how the Reynolds stresses will vary very close to the wall, that is also we have talked about. Then we talked about the the kinetic energy equation and the budget for this turbulent channel flow. Okay. So, now with this knowledge in turbulent channel flow, we are just briefly going to discuss about the turbulent pipe flow as well as the turbulent boundary layers. Okay. So, turbulent pipe flow has served since 1883 Reynolds pipe flow experiment. Okay. It served in various way in developing the understanding in turbulent flows. Okay. So, turbulent pipe flows, we can easily determine the wall shear stress by just finding out the pressure drop along the length of the pipe. Okay. So, here mainly we are going to mention key point about that, and there are ample evidences that law of the wall in fact hold goods even for pipe flow. Okay. So, turbulent pipe flow, law of the wall, that is u plus f w y plus holds good, okay, even for this case. So, and that using the log law, the way we have derived the friction law for the turbulent channel flow, in the similar fashion we can find out the friction law even for the turbulent pipe flows. Okay. So, before we proceed, there are some main symbols we need to talk about. For example, u c, just like your turbulent channel flow, u c is the center line velocity of the pipe. Okay. Center line velocity, and u v, which is the bulk velocity. Okay. And u v is defined as 1 by pi r square 0 to r u 2 pi r d r. Okay. Here that r is equal to d by 2, d is the diameter of the pipe. Okay. So, r is the radius of the pipe in that case. Okay. So, this is what is your bulk velocity, and Reynolds number defined as bulk velocity, then d by nu. Okay. This is the way we define the Reynolds number for the case of a pipe flow, right. So, with this we can use the log law to derive the friction law for the pipe, and if we find the friction law for the pipe flow, okay, okay. So, usually instead of screen friction coefficient, for the case of pipe flow, that friction factor is very often considered, which is defined as friction factor F, which is known as friction factor and F is defined as pressure drop delta P, diameter of the pipe, half rho u v square, length of the pipe. Okay. So, this is the definition for friction factor. Okay. So, traditionally friction factor is used instead of screen friction, and it can be shown that this 4 into that friction factor F is equal to 4 into Cf, okay, where Cf is the screen friction coefficient, which is defined as tau w by half rho u v square. Okay. So, these are some of the relations we need to know before we proceed. So, now using the log law, one can arrived at this particular relation log 10 square f square root of r e 0.8. Okay. So, this is what one can find. So, it is you can see from this friction law we can find F versus R E plot. Okay. So, that is what we can find from this, and this particular relation is known as Prandtl. Prandtl's friction law for turbulent pipe flow. Okay. So, this particular friction law is essentially for your smooth pipe. Okay. For this is for smooth pipe. Okay. The surface of the pipe, the inner surface of the pipe can be highly rough as well. Okay. So, in that case experimental data shows that this particular friction versus Reynolds number changes. Okay. Let us see here how does it change. So, for example, if we plot that friction factor versus Reynolds number. So, let us say this is 0.1, let us say this is 0.7, and this is let us say your 10 to the power 10 to the power, let us say this is 3, this is 10 to the power 4, this is 10 to the power 5, 10 to the power 6, 10 to the power 7, and this is your Reynolds number R e, and this curve is in log plot, that is what we would like to, sorry, this should be 0.07, okay, 0.01 and so on. So, now if you consider the laminar regime, so in the laminar regime your plot for the laminar case, this particular 16 by RE. Okay. So, for the case of laminar, the profile will look like this, and the moment it is turbulent, the profile will be something like this, and this is what is your transitional regime. Okay. So, this is what this is for laminar flow. And turbulent flow. Okay. All right. So, here there is a slight please note that there is a slight mistake here. So, it should be square root of f, and here instead of 16 it should be 64, okay, 64 by RE, and this is your friction factor f. Okay. So, this is what is the friction factor versus RE plot for turbulent pipe flow is this, for laminar case is this, and this is your transitional regime. Okay. Now, if you see your measured data here, so your measured data you see will sit like this, okay, for smooth pipe. So, for a smooth pipe your measured data will sit on this curve. Okay. So, now if you have a very rough pipe, then this is for very rough pipe, not, or if you increase the roughness of the pipe, so in that particular case you will see your data will sit like this. There will not be any change in transitional and as well as in laminar regime, whereas in the turbulent regime, with increasing roughness, that experimental data shows variation of this sort. Okay. So, if you increase even in a larger size of the roughness, once again your laminar and transitional regime will not be affected at all, whereas your with increasing the roughness height or roughness diameter, your data is going to come like this. Okay. Even further, if you increase the height, then it will be it will come something like this. Okay. The data will come like this. So, this is for increasing roughness, roughness height. Okay. So, for what it shows essentially, for increasing roughness height, your screen friction increases for high Reynolds number, that is what it shows. Okay. So, this is what the friction law. Now, we would like to we do not want to proceed further with discussion in pipe flow. We are going to now essentially talk about the boundary layer, turbulent boundary layer flows. Okay. So, we are going to talk about turbulent boundary layer. Okay. So, the simplest boundary layer we can think of flow over a flat plate. Okay. Let us draw it. Okay. So, if you consider a plate like this is what is your plate, let us say, and let us say your x is x in this direction, y is this, and z is in this direction. Okay. And if we draw the two dimensional view of this particular plate here, then this is what is our plate. Okay. And when there will be a flow over this plate, what it, there will be one boundary layer like this. Okay. Now, in this particular case, that y is this, x is in this direction, and this particular height, this is designated by delta, which is you can see increases. What is delta x? Delta x is nothing, it is the height where the mean velocity is approximately 0.99 of u infinity. Okay. All right. So, this is what when there will be a flow over a surface, there will be a boundary layer. Okay. And the simplest of these boundary layer can be considered as flat plate boundary layer. Okay. And this particular boundary layer initially very close to the leading edge, if this leading edge is very sharp, the flow will be laminar close to the leading edge. Okay. As you go downstream, the flow will start transitioning at some particular Reynolds number, and eventually the flow will be totally turbulent. Okay. So, there are some so there are some measure we have talked about, for example, the delta. Okay. So, boundary layer thickness, is based on the distance where the velocity is going to be 0.99 u infinity. Okay. So, delta is based on u infinity. Okay. So, now this particular delta is poorly defined. Why? Because it depends the velocity difference between u infinity and 0.9 u infinity. So, very difficult to measure this kind of difference close to the edge of the boundary layer. So, it is not well defined actually. So, in that particular case, there are other two integral parameters which are defined as delta star, which is you must have come across this particular integral parameter, the displacement thickness. So, this is defined as 0 to infinity 1 minus u by u infinity dy. Okay. So, this is known as displacement thickness. Okay. So, delta star is our displacement thickness. Okay. Similarly, momentum thickness is defined as 0 to infinity u by u infinity 1 minus u by u infinity dy. Note that capital U is essentially our main velocity. So, theta is actually momentum thickness. Okay. So, these are the kind of integral parameter for this boundary layer flow. Okay. Now, if we consider two dimensional laminar boundary layer, then two dimensional laminar boundary layer equation is very simple. Let me just quickly write it for our better understanding of turbulent boundary layer flows. Okay. So, this is what is the complete Navier-Stokes equation for steady two-dimensional two-dimensional flows, okay, not bondular, steady two-dimensional flows. This sort of equations, will be useful. Now, we are going to talk about, bondular, means the viscous effects close to the wall is significant. So, if you draw the velocity profile somewhere here, it is going to be something like that. Okay. So, there is a sharp change of velocity along the y direction. Similarly, if you draw another velocity profile here, somewhere here, the velocity profile will look like this, okay, and so on. If we draw somewhere here, then also it is going to be something like this. So, from this we see that the cross stream variation significant as compared to the variation in the streamwise direction, okay, of the velocity. Okay. From this velocity profile itself you can make it out. So, here the del x is much less than del y term, or del 2 del x 2 is much less than compared to del y 2. Okay. So, this is one point to mention for these bondular flows. Another point to note is that you see we are talking about bondular flows, means the viscous activities close viscous activity very high close to the wall, because bondular means the velocity at the wall is 0 and within very small distance away from the wall the velocity is going to be equal to the free stream velocity. So, within this very thin layer the viscous activity is very dominant. So, in that particular case what we are talking about essentially, we are going to talk about that this inertial effect and this is what is your viscous effect. So, that since we are talking about bondular means the viscous effect is strong, okay, that means this viscous, the leading viscous term should be of the order of the leading convective term, okay, or your inertia term. Okay. So, what it says this inertia term, if you consider the order of magnitude, so u square by L should be of the order of your sorry, there is a mistake here. So, order of the leading order viscous term. So, which is going to be your u infinity by let us say y scale, the appropriate scale for the y, it is going to be bondular thickness delta square. So, that means this is going to give you the relation delta by L of will be varying as delta by L will vary as if you so one nu should be there. So, because that nu is here. So, the delta by L will vary as square root of R E L. Okay. Why? You see delta square, okay, by L square if you take, then you are going to have here what nu divided by u infinity into L. So, that is nothing but your this. So, that means if you increase your Reynolds number, your bondular thickness is going to be smaller and smaller. Okay. So, this is what one important point to note for the case of bondular flows. Okay. So, that means in this particular case the delta varies as the bondular thickness varies as L into square root of R E L. Okay. That is the way it changes. L is the can be considered as the length of the plate here. Okay. So, now and one more point to note that if you consider the pressure distribution over any body over which the flow is going on, then that pressure distribution can be approximated using your irrotational flow approximation. Okay. So, that means whatever the pressure distribution will be, if the flow is irrotational, same pressure distribution can be approximated, can be considered as the pressure distribution even for this for this viscous case close to the wall. So, that is because of the fact the pressure is impressed from the free stream on the in the bound layer. So, that means outside of the bound layer, the equation which governs the flow, that is your Bernoulli's equation, P plus half rho U infinity square is equal to constant. That means what I would like to say, that outside P infinity plus half rho U infinity square is equal to constant. So, from this we can say that pressure of the pressure is actually your rho infinity square. Okay. Pressure scales as this. Okay. So, that means if you consider your non-dimensional pressure as P minus P infinity by half rho U infinity square or just rho infinity square, okay, and your y as y by delta or x prime is equal to x by L, okay, x by L, and your u prime, which is the non-dimensional quantity, that u divided by u infinity, and v, which will come from the continuity equation. If you find out the scale for v, that is going to come your u infinity delta by L. Okay. So, with these scalings, if you go ahead with the non-dimensionalization of this particular equation, then I am not doing this exercise considering that the fact that I am just giving a brief overview what we already learnt about this technique. So, then we will be able to write this equation as this prime 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 prime, and this is going to be del p del y. Okay. I am sorry. So, then this quantity is going to be essentially prime, okay, and this quantity is going to be 1 by R e square, okay, and this is prime, and this quantity 1 by R e. Okay. Similarly, this equation is going to be prime prime prime, and with this scaling, if you non-dimensionalize that equation, this is what is going to come, and this quantity is going to be 1 by R e, and this is will remain as it is. So, this is going to be prime. Okay. So, here it should be prime 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 prime. Okay. So, now we are talking about a boundary layer flow, means that high Reynolds number case. Okay. So, when Reynolds number is your high, so from this equation, what do you get? You get that del p prime del y prime is equal to 0. This is what is your x moment y momentum equation shows, and your x momentum equation will show that this particular quantity will go. So, essentially your boundary layer equation is this. Okay. So, this is what is your boundary layer equation. Okay. Based on this based on this understanding or based on these skills, we can simplify the two dimensional Navier-Stokes equation as this for boundary layer flows. Okay. So, anyway, now we are considering the turbulent boundary layer. This is for the laminar boundary layer case. So, we are going to talk about the turbulent boundary layer. So, this will be useful. So, there is similarity solution of this equation for flat plate case. So, for flat plate case, the previous boundary layer equation will have a similarity solution which is done by Blasius. So, his name as per his name, it is called Blasius solution. So, based on this Blasius solution, we will have various relations. For example, for a laminar boundary layer, Blasius solution says that delta is approximately 5 into or in some you can consider 4.9 into nu x by u infinity. Okay. So, this is one relation, and another relation your CF, okay, the screen friction coefficient which is given 664 divided by square root of R e x, okay, where that R e x is nothing but your u infinity x divided by nu. Okay. So, these are the relation for Blasius boundary layer. Okay. So, these well known relations, and if you consider now, if you consider your that shear stress and velocity profile, then it will come something like this. Okay. So, this is let us say 1. So, your this is about 5, this is 6, okay, this is 7 and this is 0, then 1, 2, 3, 4. So, this is 1, 0.1, 0.2, 0.3, 0.4, sorry, this is 0.2, 0.4, 0.6, 0.8, okay, this is 1, and your velocity profile, the Blasius velocity profile will look like this. Okay. So, this is your basically u divided by u infinity, okay, and this profile your tau v t divided by tau w. Okay. So, v t means essentially in this particular case Reynolds stress part of this v t is equal to 0. So, only will be left with the viscous part of that. So, this is what the variation in for the case of laminar case. Okay. So, this is for laminar case. Okay. And if you consider the similar variation for the case of turbulent, then you will see so for the case of turbulent, let us say this is 1, this is 0, 0.2, 0.4, 0.6, 0.8, okay, 0.2, 0.4, 0.6, 0.8, and this is what is your. So, sorry to mention here, it should be the Blasius scale or that is y, this should be y divided by delta, where a delta has been considered here square root of nu x by u infinity. Okay. That is what is delta in this particular case. Okay. So, this is let us say the Blasius scale. Okay. So, in this particular case, if we plot the velocity profile, then you will see the velocity profile is flatter close to the wall. Okay. Close to the wall, that velocity profile will be flatter like this. Okay. And if you consider that shear stress is going to change as this. Okay. And if you consider your intermittency profile, which is going to come something like this. So, this is y by delta, okay, and this is this is for u by mean velocity divided by u infinity, and this is your intermittency function gamma. I have already introduced this quantity while talking about the free shear flows. Okay. So, please do understand this is what is our intermittency function, which is maximum value is 1 and the minimum value is 0 somewhere outside of the mean boundary layer. Okay. And this is your tau v t divided by tau w. Okay. So, this is what is your tau v t by tau w. Here in this particular case is tau v t is given by rho nu del u del y minus rho u v bar. Okay. So, that is what is your tau v t. So, from these two equations, so this particular profile is for turbulent case, okay. So, this is laminar case and this is turbulent case, and here if you see, if you compare the shear stress profile. So, shear stress profile something similar, okay. What about your velocity? So, velocity profile if you consider, see this particular turbulent velocity profile is flatter close to the wall as compared to the laminar velocity profile, okay. And this flatness is measured by some quantity called shape factor, okay. So, shape factor h, which is defined as delta star the displacement thickness divided by momentum thickness, okay. So, this is known as shape factor, okay. So, that shape factor value for a laminar case, okay, for laminar case it is going to be 2.6 approximately, and for 0 pressure gradient turbulent case it is going to be approximately 1.3, okay. So, age can be considered as shape factor, which also can be considered, as the sort of this measure of this flatness of the velocity profile, okay. So, that is what it says, all right. With this I just wanted to mention some of the differences we notice for the case of turbulent bound layer as compared to your turbulent channel flow. So, there are mainly three differences which can be noted, okay. So, the first one is that as compared to your channel flow, the bound layer thickness continuously increases in the downstream direction, okay. So, as compared to channel flow, you see your bound layer thickness here, so this quantity bound layer thickness is continuously increases as you go downstream. So, this is sort of developing as compared to your channel flow, all right. So, this is one point, the bound layer thickness. So, as compared to channel flow, bound layer thickness continuously increases in the downstream direction, okay. This is one point. Another point is that in the case of turbulent channel flow or turbulent pipe flow, in the case of turbulent pipe flow or turbulent channel flow, if you remember that we know dPw dx equals to tau w by delta. Delta was the half channel height in the case of turbulent channel flow, okay. If you write the same expression, similar expression for turbulent pipe flow, then you will be able to write minus dPw dx equals to tau w by r into 2, okay. I think this should be positive, instead of this is x, it should be r, okay. So, this is for turbulent pipe channel flow, and this relation also can be derived considering the momentum equation in polar coordinate system, okay. So, this two relation, from this two relation what we can find, so from this no, this should be in x only. Okay. So, from this two relation what we can find, if we can measure the pressure drop along the length of the pipe, essentially we will be able to find out the wall shear stress. That is what it says for both the cases. Now, measuring pressure drop along the length of the pipe or length of the channel is much easier, and from that you can easily find the the tau w, that wall shear stress or spring friction coefficient from this. Okay. This is not the case for the case of turbulent boundary layer. So, so that means tau w is not non a priori. Okay. It is not known a priori, tau w for the case of boundary layer. Okay. And another point, as I have mentioned, the intermittency. Okay. So, turbulent boundary layer turbulent boundary layer is intermittent towards boundary layer is. Okay. What it says that if you consider a turbulent boundary layer, let me just give what I would let me just give you the brief overview of intermittency, what I would like to mean here. So, towards the outer side of the turbulent boundary layer, so let us say it is a turbulent boundary layer, okay, it is highly chaotic in nature. Okay. So, so this is what is our turbulent boundary layer. So, if you put a probe, somewhere here, let us say if this is your probe somewhere here, then what it will happen, that probe sometime the probe will encounter the outside irrotational flow, sometime that probe will encounter the rotational flow within the boundary layer. As a result, the signal of the probe towards the outer side will look something like this. Okay. So, what it says, when the probe is hit by the turbulent packet, it will show the high fluctuation. When it is hit by the irrotational packet from the free stream, then the signal will be more quiescent. Okay. That is what it says. So, that means that for this delta t 1, let us say this is your delta t 2, so delta t 3. Okay. So, if this is your entire time, capital T, then your intermittency gamma is nothing but summation of this delta t divided by total t here. Okay. And this quantity, if your probe is well within the turbulent boundary layer, it is always going to be turbulent, because your irrotational side is much above from this probe location. Okay. As a result, it is always going to face the turbulent packet only. Everywhere it will be turbulent for this particular probe. Okay. So, the signal for this particular probe is going to be all the time like that. So, your intermittency is for this kind of signal is going to be always 1, as you can see here, that intermittency close to the wall, close to the wall, the intermittency here always 1. Okay. Later on it keep changes, okay, as you are coming towards the outer side of the boundary layer. So, these are the main 3 kind of differences. So, although these differences are there, but we kind of there are many references that law of the wall holds good even for the case of turbulent boundary layer. Okay. So, although these differences are there, the law of the wall hold goods even for the case of turbulent boundary layer. Okay. So, that measurement measurement as well as the computation shows the following type of velocity profile in a turbulent boundary layer. Just let me quickly rub it out and let me show you the variation of these So, if you plot your velocity profile in a turbulent boundary layer, so let us say this is 30, okay. Let us say this is 0 and this is your let us say 1, this is your 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4 and so on. Okay. And let us say this is 1, this is 2 and maximum is 30. Okay. Or let us say this is 1 and this is 5, then this is 10, this is 15, this is 20, 25, 30. Okay. So, if you plot your velocity profile, you will see let me use other color. So, your velocity profile in this particular plot. So, this is the log scale. Okay. So, this is your y plus and this is your u plus. Okay. So, if we plot this data either measurement or your computational data, which is found to be like this. For example, the DNS data for turbulent boundary layer shows something like this. Okay. Let us consider this is a broken curve. Okay. Like this. Okay. And if you put your measurements, that also kind of shows sorry, let me use if your measured data if you use, that also will seat something like that, then later on it deviates from this straight line. Okay. The question is, since the inner law holds good, that is u plus function of f w y plus holds good for inner layer, that is y by delta less than 0.1. Okay. So, for the case of law of the wall for the boundary layer also, this u plus is equal to y plus, okay, u plus is equal to y plus within this regime, and later on from y plus 30 or 50 onwards your log law kind of holds good, right. So, that means from your 30 or 50 onward, let us say this is your 30 y plus. So, y plus 30 onward your log law, this is what is your log law holds good. Okay. So, and this is what is your u plus is equal to y plus curve. Okay. Question comes, then what happens between this y plus is equal to 5 to y plus is equal to 30, okay, which is known as buffer layer. So, what will be the shape of the buffer layer, okay, or what will be the functional form, this functional form. Okay. This functional form is in the viscous sublayer it is u plus is equal to y plus, and in the log layer it is actually u plus is equal to 1 by kappa ln y plus plus beta. That is what we have learnt. Question we asked here, what will be the functional form of that. So, that can be argued from this particular or Van-Drist, okay. Van-Drist argued as follows, okay. So, u plus is equal to y plus, which holds good in the entire layer. So, your tau v t he argued in this fashion, tau v t can be written as this del u del y minus rho u v, right, or this can be this can be written as tau v t divided by rho equals to nu del y, and this that Reynolds stress, this quantity you can write as nu t del u del y, okay. Your nu t is eddy viscosity, okay. So, this nu t is eddy viscosity. Now, using your mixing length hypothesis, we can write this as nu del u del y plus L m square del u del y whole square, okay. This is using the Prandtl's mixing length hypothesis, okay. So, if you use the inner variable for normalization of this particular relation, then we can write this relation as tau v t tau w, that will be your del u plus y plus, okay. This is L m plus and L m plus whole square del u plus y plus whole square, okay. So, this is what we can write, okay. Now, this equation from this equation you see we can find the solution of this derivative, because it is a quadratic equation of this derivative. So, we can find the solution of this equation. So, that means u plus del y plus is equal to, we can write as twice tau v t tau w, okay, one plus 4 tau v t tau w, okay, L m square to the power half, okay. So, the solution of this equation can be written as this, okay. Now, very close to the wall, tau v t by tau w can be considered to be 1, okay. Very close to the wall, this can be considered to be 1. So, in that particular case, your equation becomes, let me write it here. So, very close to the wall, your del u plus del y plus can be written as 2 1 plus 4 L m plus whole square, okay, to the power half, all right. So, from this you can find u plus is a function of y plus, okay, where that f w y plus can be given as integration 0 to y plus dy 1 plus 4 L m plus square half. Note that Lm plus is a function of y itself, okay. Because if you know that in the logarithmic layer the Lm can be written as kappa y. So, Lm plus is nothing but your kappa y plus, okay. So, Lm is a function of y you know, in the logarithmic layer, this is what can be considered, okay. All right. Now, so this is the equation and F w is given by this, okay, as per the mixing length theory, okay. But if you consider, I have removed this relation, let me just write this relation once again for complete argument. So, what we wrote V t by rho is what? Tau V t by rho we wrote nu del u del y plus nu t del u del y, okay. This is what using that eddy viscosity we wrote, all right. So, or nu del u del y plus this can be written as Lm square del u del y square, right. And if you see, this is your Reynolds stress quantity, okay. This is your Reynolds stress quantity, and in the if we consider that Lm even closer to the wall as closer to the wall also, that Lm is considered to be kappa y, then you see this is actually is what? Reynolds stress. So, then it will vary as y square, even very close to the wall, as per the approximation Lm is equal to ky, sorry, kappa y. But we learnt while talking about channel flow that this variation is slower, that means it varies as this, okay. So, to impose this slower variation, Van Drijst what he did, he used a damping function, okay. He used a damping function. So, for that he used that Lm plus is equal to kappa, he used this particular damping function instead of y plus he used y plus 1 minus 1 minus minus y plus by a plus, okay. A plus is some constant, okay. So, if you see what is going to happen when your y plus value is very large or large, then that Lm plus is going to come as kappa y plus itself, okay. But when y plus value is less, this is not the case, then this Lm plus is going to be damped by this introduction of this function. So, this is known as Van Drijst damping function. So, now if you consider this expression in this equation and you integrate this, that integration that will give you that particular profile will give you, you see this is what is going to give you, okay. So, this to approximate the data or the experimental observation within the buffer layer, that Van Drijst introduced the damping function, okay, for this mixing length hypothesis. Okay. And using this function, if you integrate the f w y plus closer to the or in the inner layer, then you are essentially able to recover the experimental observation, or you are able to express the able to predict the experimental observation. Okay. So, that is what actually he has done in that particular case. Okay. So, all right, this is what we have learned from this particular exercise. Now, what will be the shape of velocity defect? Okay. Because if you see here, this is your log law. So, in the outer side of the boundary layer, the experimental observation or your computational data shows that it departs from this log law profile. That means, in this particular regime, your velocity profile is not going to be recovered by this log law, then something else needs to be found out. So, what Coles, the Coles decoals. So, what he did, he observed or tabulated many experimental data and found that the experiment found that velocity profile, the velocity profile can be written as u by u tau can be expressed as a function of y by delta v plus some so the velocity profile can be written summation of this function plus this function. So, the velocity profile can be expressed using these two function, the complete velocity profile. Today I do not have time, so I will consider this particular discussion in the next class. Okay. So, I would like to stop it here for this particular class here. So, in the next class we are going to talk about the defect law as well as the turbulent kinetic energy equation for this turbulent boundary layer. Okay. That is all. Thank you.